Welcome to the second lecture of electronic devices. In our last lecture, we have studied about first category of the semiconductor, that is elemental and compound semiconductors. In today's lecture, we are going to study about energy balance structure of semiconductor. So, first of all, we take a case study of silicon or carbon semiconductor. We know that X-ray and other studies reveal that most of the metals and semiconductors are crystalline in structure. A crystal consists of space array of atoms or molecules built up by regular repetition in three dimensions of some fundamental structural unit. The electronic energy levels discussed for a single free atoms, as in gas, where the atoms are sufficiently far apart not to exert any influence on one another, do not apply to same atom in a crystal. This is so because potential characterizing the crystal line structure is now free to function in space, whose value at any point is the result of contribution from every atoms. When the atoms form a crystal, it is found that energy levels of the inner cell electrons are not affected appreciably by the presence of the neighboring atoms. However, the levels of the outer cell electrons are changed considerably since these electrons are shared by more than one atoms in the crystal. The new energy levels of the outer electrons can be determined by means of quantum mechanics. And it is found that coupling between the outer cell electrons of the atoms results in band of closely spaced energy states instead of widely separated energy levels of the isolated atoms. So, first of all, we discuss the qualitative discussion on energy band structures. So, consider a crystal consisting of n atoms of one of the elements in the table. The table is described here. We can take any of the material to consider or discuss for this particular study. Imagine that it is possible to vary the spacing between atoms without altering the types of fundamental crystal structure. So this is our first assumption. So if the atoms are so apart that the interaction between them is negligible, the energy levels will be coincide with those of isolated atoms. The outer two subcells for each element in the table, this is the table, contains two s electrons. So we are seeing here that we are having two s electrons and two p electrons in their outermost cell for every element that are here in this particular table. Hence, if we ignore the inner cell levels, then as indicated in the extreme right of figure A, this is the figure A, there are two n electrons completely filling the 2n possible s levels. That 2n electrons are completely filled the s levels. Here we can see in this figure, all at the same energy. So these s electrons all have the same energies. So there are, since the p atomic subcells has 6 possible states, so our imaginary crystal of widely spaced atoms has 2n electrons, which will fill only 1/3 of the 6n possible p states. So we are seeing here that we are having 2n s electrons and 2n states. 6n states, it is completely filled. It is filled by 2n p electrons. So we are having separate energy levels when the interatomic distance is very high. If we now decrease the interatomic spacing of our imaginary crystal moving from right to left, so we are going to right to left, then an atom will exert an electric force on its neighbor. Because of this coupling between the atoms, atomic wave functions overlap. So these are the overlapping we are seeing here. So we switch to figure number 2. So we can see here our overlapping goes on, and the crystal becomes an electronic system which must obey the Pauli exclusion principle. Hence the 2n degenerate state must spread out in the energy. The separation between levels is small, but since n is very large, it is around 10 power 22 per centimeter cube. The total spread between the minimum and maximum energy may be several electron volts. So if the interatomic distance is decreased sufficiently, so this large number of discrete but closely spaced energy levels is called energy band. So we can see here that if the interatomic distance is decreased significantly up to the crystal lattice spacing constant, so these are the particular energy levels we are seeing here. In this figure, the 2n states in this band are completely filled with 2n electrons. Similarly, upper states region in figure 8 in the bands of 6n states has only 2n of its level occupied by the electrons. So all the energy levels are merged here at this point. So we are having total 8n states, 6n plus 2n. So out of 8n states we are having total 4 electrons. So incompletely we are dividing these states into a particularly 4 electrons. So we are having about of 4n electrons empty states. Note that there is an energy gap between the two bands discussed above, and this gap decreases as the atomic spacing decreases. So under such circumstances, 6n upper states merge with 2n lower states, giving a total of 8n levels, half of which are occupied by 2n plus 2n 4n available electrons. At this spacing, each atoms have given up 4 electrons to the bands. These electrons can now no longer be set in orbit of s or p subcells as an isolated atom. So in this sense, the elements in table are tetravalent since they contribute 4 electrons each of the crystal. The band of each electron occupied is called valence band. So this is our valence band and this is our conduction band. So if the spacing between atoms decreases below the distance at which the band overlaps, the intersection between the atoms is indeed very large. The energy band structure that depends upon the orientation of the atoms relative to one another in the space and upon the atomic number, which determines the electrical constitution of each atom. So the solutions of Schrödinger equations are complicated and have been obtained approximately for relatively few crystals. These solutions lead us to expect an energy band diagram somewhat as pictured that described in figure B. At the crystal lattice spacing, the dashed vertical line, we find the valence band filled with 4n electrons separated by a forbidden band of extent Eg for an empty band consisting of 4n additional states. So this Eg is called forbidden band gap. So we are drawing a particular vertical line on this particular plane. So we are talking about on this valence band and this conduction band. So this upper vacant band is called conduction band. So this is the particular energy band diagram of the semiconductor, we can say. Next is insulator, semiconductor and metals. A very poor conductor of electricity is called an insulator. An excellent conductor is a metal, and a substance whose conductivity lies between these extremes is called semiconductor. A material may be placed in one of these three classes depending on its energy band structure that we have studied in our previous slide. So first of all, we need to talk about insulator, then semiconductor, then metal. So for insulator, the energy band structure as shown in this figure, at the normal lattice spacing is indicated systematically. For a diamond or carbon crystal, the region containing no quantum states in several electron volts, that is, this is the forbidden band gap here in this particular diagram. In this, forbidden band gap is around of 6 electron volt or above. This is called forbidden band gap. This is conduction band, this is valence band. These are the rectangular shaped notation of previously studied energy band diagram because its drawing is very easy. So this large forbidden band gap separates the filled valence region from the vacant conduction band. The energy which can be applied to an electron from an applied field is too small to carry the particle from the field into the vacant band. Since the electron cannot occupy sufficient applied energy, conduction is impossible. Hence, diamond is an insulator. So we can see here the forbidden band gap is very high. So the electrons or any electrons carriers cannot move to conduction band until or unless they get this particular amount of energy. So this particular structure denotes the energy band diagram of insulator. Semiconductors, so this is the energy band diagram of semiconductors. In semiconductors, a substance for which the width of forbidden energy region. So we can see here energy band gap region width is order of 1 electron volt is called semiconductor. So graphite, a crystalline form of carbon but having a crystal symmetry which is different from diamond, has such a small value of Eg, and it is semiconductor. The most important practical semiconductor materials are germanium and silicon, which has value of this particular energy band gap is 0.785 and 1.21 electron volt respectively at 0 degree Kelvin. So energies of this magnitude normally cannot be acquired from an applied field, hence the valence band remains full, the conduction band empty, and these materials are insulated at low temperature. However, the conductivity increases with the temperature, so these substances are known as intrinsic semiconductor. Next one is metal. Next structure is metal. A solid which contains a partly filled band structure is called a metal. Under the influence of applied electric field, electron may acquire additional energy and move into the higher state. Since these mobile electrons constitute a current, the substance is a conductor and the partly filled region is the conduction band. So we can see here that in this particular figure, the conduction band and the valence band overlap with each other. So this diagram is for metal. So this is the energy band structure of insulator, semiconductor and metal in the notation format, similar notation format. So what next? In next class we are going to study about what the semiconductor and how the semiconductor can be classified. These are according to degeneracy, non-degeneracy, and their band gap structure type. Thank you.